In this video, we'll discuss the dawn of modern mathematics. Now, we consider it the dawn from the late 1500s to the 1600s because of the amount of innovation that occurred both in math and science. We see the codification of symbolic algebra and the development of logarithms, which greatly enhanced both the mathematics and science of that time period. Within science, we have the science of dynamics and motion being developed, as well as a better understanding of the universe for which we live. Additionally, we see great enhancements both in geometry, analytic geometry, probability, and in the late 1600s with the development of calculus. So that's a lot of different innovations that occurred in such a short period of time. Within algebra, we see several different key figures that helped after Vieta. For example, William Oughtred helped produce over 150 symbols that were used in that symbolic algebra, as well as showed how to use algebra to solve problems. Some of those symbols we still use today. Thomas Harriot was important in England as he helped found the School of Algebrists, and the textbook that he constructed provided that foundation for which we create our own textbooks now. He also provided some symbols that helped enhance how we do powers as well as inequalities. Additionally, Albert Girard helped fund the fundamental theorem of algebra, which states that for any polynomial equation, the degree must match the number of solutions, which meant that they could understand there had to be complex solutions to some polynomial equations. At the same time, we have the development of logarithms, starting with John Napier, who was both a mathematician, a theologian, and an inventor. Well, when we think about the logarithms that Napier discovered, none of them had the understanding of exponents at that time. So what they did recognize is that to calculate many of the large calculations needed in astronomy, it was huge numbers that took lots of time and would make many errors because of how big they were. So he focused then, instead of saying, how can I create an arithmetic measure that follows a geometric measure? And it took over 20 years for him to develop it. From that came two specific books on logarithms, which were widely read around Europe. And they were adopted both in Europe and in China. Laplace at the time said that Napier's work helped shorten the labors of calculation so much that it doubled the life of astronomers. And Kepler then used his logarithms to help improve his astronomical work with his laws of heavenly bodies. Now, Henry Biggs read the works of Napier and then went and met with Napier before he died. Together, they started to collaborate on creating the logarithmic tables of base 10. And it was the works of Briggs that then completed that work after Napier passed away. He used the help of Adrian Bloch to help him complete the gaps of where his works were done, and so that by 1628 we had a book of tables from 1 to 100,000 that was used until 1924. And the reason it stopped being used in 1924 is because a book with larger values was then included. Now, we think about what it is that makes a logarithm, and we use the equation that the log base a of x equals y. We define that as an exponential equation of a to the y equals x. And what is important to recognize with this is that that exponential equation was not developed for quite a number of years after Napier and Briggs, so their construction of logarithms came before their understanding of exponents. Now, with the discovery of logarithms came the need for tools to help with that beyond the book of tables. Edmund Gunter created a scale line that did use proportional numbers in their logs to then do multiplication, division via addition, subtraction, but it did require a pair of dividers. However, then William Oughtred created the first simple slide rule, and Delamain created the circular slide rule about 7 years later. Now, slide rules were then used for the next several hundred years, but they were standardized by Mannheim around 1850. And until the late 1970s, slide rules were prevalent tools, as well as the book of logarithmic tables. And think about what we did in that time frame. We flew man to the moon and did all of our works with NASA using slide rules. No calculators at that time. So that's quite a fascinating feat, what can be done just with this tool. Now, how would logarithmic multiplication been done? First thing we do is we take two numbers, say 325 times 1720. We convert them to scientific notation. So this would be 3 1/4 times 10 to the second and 1 7200 times 10 to the third. Now we would use the logarithmic table, or in our case, we can use our calculator with the log button. And we would then find those values for that smaller value, the 3 1/4 and the 1 7200. The log tables would give us these values. We add them together. and then that gives us 747,411 millions. Now, what we would then do is take 10 raised to that value. This would be placed in the log book as well, and that would give us about 1 in 18,779 hundred thousandths. Now we go back to our exponents in the scientific notation and add them together. It's important to recognize that if you did subtract 1 in this sum right here, that will be added to the exponent. In this case, we didn't, so that would just be 10 to the 5th. So now we multiply our 10 to the s by our value here, and we would get 558,998 and 96 hundredths. And if you did this with just your basic calculator, you get 559,000. So look at that, we're within 1 and 4 hundredths using this method from hundreds and hundreds of years ago. Now, there are many mathematicians and scientists of the 1600s that were greatly influential to our time now. For example, Stephen Hawking thinks that Galileo was probably one of the most important people to the birth of our modern science. He provided many of his connections, both theories to using experiments, and then would refine them based on what he would learn from his experiments. He initially did study medicine, but while watching pendulums swing up in a cathedral, he had to start thinking about what was going on mathematically. And that desire to understand what was occurring led him to instead studying mathematics. By the age of 25, he became a professor at the University of Pisa, and he would perform his experiments publicly to show especially that falling bodies would fall at approximately the same rate regardless of their weight. And that led to his famous formula that the S equals gt squared over 2. And however, this work that he did went against much of the understandings of Aristotle of that time, which was well regarded. And that led him to leaving the University of Pisa and going to the University of Mantua. While there, he also then constructed a telescope, which was originally funded for military use, but then he recognized how to continue to refine it. And by his 5th iteration, he was able to observe heavenly bodies and look at our universe and our solar system. For example, he's able to see 4 of Jupiter's moons, Saturn's rings, sunspots, mountains on the moon, and many other things, including parts of Venus. However, this work led him to get himself into trouble because it helped to prove much of the Copernican theory about smaller bodies revolving around larger ones. When he published his works, he was then pulled into the Inquisition, and they forced him to recant his scientific findings and put him under house arrest for the rest of his life. The book was then placed in the Index of Prohibited Works for over 200 years. However, the work that he did had already been publicized and was well regarded, so that the Copernican theory and his works with it continued to be spread throughout Italy and through Europe. Now, at the same time, we have Johann Kepler, who was building the work of Tycho Brahe and Copernicus. And he was in a different part of Europe, which then allowed him to continue his works without being persecuted by the church like Galileo. With his works, he was able to construct the 3 laws of planetary motion, and these were important and foundational for much of the work that came after that. Now, what was important about his work too is that he would write not only about the laws, but he would write about the works and the experiments he would do to how he would get to his theories. And it showed a way that scientific method could start with a theory, use experiments, and work to determine were those measurements matching up, and then to revise your theory based on what you're learning. Additionally, his works became the precursor to calculus, as he had to use rudimentary forms of integrals to help understand the areas of the elliptical curves. And finally, we'll talk about Blaise Pascal, who is considered one of the greatest might-have-been mathematicians. The reason we say might-have-been is because he lived to only be 39, and he was a brilliant mathematician of that time. He had a wide range of works and was part of the French Mathematician Guild early in his teenage years. By the time he was 18, he created a calculating machine and created 50 different versions of it before his death. He also created works in hydrodynamics, where we have Pascal's principle. He did works in mathematics as well, such as in conics, the cycloid curve, and as well as projective geometry. And he also did significant work with Fermat in founding of probability. Now, part of how he was able to do his probability was using Pascal's triangle, which was used both for binomial expansion, probability, and the number of combinations in a set. Now, it's important to recognize, why do we call it Pascal's triangle? And part of it is because he was the first to discover it in Europe. And so for hundreds of years, no one actually knew that other civilizations prior to Pascal had been utilizing it as well, such as the ancient Chinese civilizations. So for that reason, it has received Pascal's name over the years.